We'll continue calculating the surface area of a 3D model, and whatever we have seen, so we would proceed further to it. Sometimes you feel that mere doing a calculation of surface area of a model, you tend to use everything that you have learned in calculus. So calculus, where you have a kind of a chance to kind of do so many things. So calculus is not like only integration. It begins from integration. Calculus begins from integration, but it continues till differentiation, differential equation, then kind of partial derivation, and so many things. So calculus is not only integration; it is so many parameterized, parameterized vector, and then vector field. So in the calculus, so many things that comes into the picture. So there is one place that at least I am seeing where we can use vector, we can use a kind of everything, almost everything what someone can use in calculus in computing the surface area of 3D. So that is the concept. So what we have calculated till now. So if I see calculation of kind of whatever we have done, now calculation of surface area. So we have first we calculated the curve length. If I have a circle, if I have a circle, then what is the curve length? That is the parameter of the circle. So that we have calculated pretty nicely. Then we calculated the surface area of a sphere through pure Cartesian coordinate and through hybrid Cartesian and polar coordinate. Okay. So pure Cartesian coordinate is our approach, and someone can proceed on it. So if he is not able to do or something, then he is open to proceed on it. So if we see that if I have a sphere, now we start the discussion. I have a sphere. I have a sphere. Now this sphere is centered at origin. This sphere is centered at origin. So top hemisphere is above the xy plane and bottom hemisphere is down the xy plane. Now if I take any point on the surface P, then what is the position vector from the center to P? That is xi plus yj plus zk, or xi plus yj plus fxy k, where this is x-axis, this is y-axis, and this is xy plane. If this is xy plane, then I have set of xy point. On that point, I have the complete hemisphere. Those points are nothing but they belong to a closed region, that is a circle. So circular closed region is the xy plane, and based upon those points I have fxy. If I connect all the points fxy, it creates a surface. Okay. Now if that is the case, then if I take any point P, from origin, if I draw a vector, position vector, that is xi plus yj plus fxy k. Now at this point P, what is dp by dxy plane? This is what we are seeing. dp by dxy plane. dp by dxy plane means now we came to a situation where I have earlier I had two independent components, x-axis and y-axis. More detail on independent component, please see the previous videos. Mandatorily required. So we have x-axis and we have y-axis, we have xy plane. Now if I have a point P And if P is shifting from one place to another place, if P is here, this proves that there is a shift in xy. Means there is a shift in xy value on the xy plane. If I consider one independent variable, that is xy plane, not x-axis and y-axis, two independent variables, x and y. One independent variable, that is x comma y, that is whatever is the combination of x comma y, that is one value. So we have xy plane. So if there is change in x comma y, then how much we change we see in p, dp by d x comma y, dp by d xy plane. Okay, so dp by dx comma y dp, change in position vector with respect to one unit change in xy point, that is one unit change along xy plane, not x-axis or y. This is dp by dxy plane. If that, if I am able to calculate that, then what is dp by dxy plane? So we talk that dp by dxy plane is nothing but a tangential surface. dp by dxy plane, if it is p here, then dp by dxy, dp by dxy plane or dp by dA means area, then it will result in tangential surface everywhere. Wherever I move p, then p vector is from origin, then there is a radial vector passing through p, that is p vector, that is also called position vector. But at position vector p, if I calculate dp by dxy plane, whatever the algebraic equation, whatever vector I am receiving in form of algebraic equation called vector field, whatever vector field I am getting, that is nothing but vector field of tangential surface at that point. If I keep changing p and calculate dp by dxy plane, I'll keep moving the tangential surface. This is what we saw. Now, if I have a circle, if I have a circle, if I have a circle, then if this is point P, then this is position vector. If this is point P, then this is position vector. Keep changing P, position vector would change. Okay, but there is only one independent component called x-axis. dp by dx. Change in P, the unit of change in P is seen when there is one unit change along x-axis. That is the case, then dp by dx is tangent at P. If P is moving like this, then tangent would move like this. So tangent is moving like this, the way dp by dx is moving. If I want this tangential line length, then I have to calculate magnitude of dp by dx. If I integrate dp by dx back, it gives me position vector. But if I calculate the magnitude of dp by dx, that is velocity vector or vector field, then I get back the length. Okay, so if I integrate velocity, then I get back the distance. If I differentiate distance, I get the velocity. So if I have dp by dx, it is a velocity vector. It's a vector. If I calculate this velocity vector magnitude, and then if I integrate, I get the net length, net distance. Okay, because vector, if I integrate vector, I'll get the position vector back. This is what we don't want. I have a position vector which is x component, y component, z component. If I do dp by dx or dp by dxy plane, I'll get a velocity vector. That is a tangential surface. In 2D, it is tangential line. In 3D, it is tangential surface. That is velocity vector. Now, if I integrate the velocity vector back, I will get back the position vector. But if I calculate the magnitude of the velocity vector, then it would result in an algebraic equation. Now, if I integrate the algebraic equation back, then I will get another algebraic equation, that is the length. Okay. Length means from the point I started. Like I always talk, a person is started from a point and he is walking at a speed per hour, means kilometer per hour, that is x. X means or that is t. T is the time. So at time 1 hour 30 minutes means 1.5 hour. At that time his speed is 1.5 kilometer per hour. At time 4.5 hour, at that moment his speed is 4.5 kilometer per hour. So his speed is proportional to the time. So the equation is t. Now how many kilo? Now velocity is t. Velocity is not 3 kilometer per hour. It's not constant. It is t. In algebraic equation. If velocity is t, then how much distance he has collected up to 4 hours. So integration of t, that is t square by 2. Again, the distance what he has covered, it came in algebraic equation. Speed is in algebraic equation. Distance what he has covered is in the algebraic equation. So t square by 2. At the end of 4 hours, he has traveled 8 kilometers. So if I have dp by dxy plane, d position vector by dxy plane, this is velocity vector. This is not algebraic equation. This is a vector where x component, y component and z component, they are algebraic equation in terms of x and y. So this is also called velocity vector because we have calculated the velocity. Or it is called vector field. If I have a vector field and I want the length by integrating the velocity vector, then I have to calculate the magnitude of the vector field. If I calculate the magnitude, I get a single algebraic equation, the way I gave the example now. If I have a single algebraic equation, then if I integrate it, I get length algebraic equation. Now keep changing the xy, you get the surface area. I will get, if it is 2D, then I'll get length algebraic equation. If it is 3D, I'll get area algebraic equation. So dp by dxy plane would give vector field where x, y and z component are there of the vector field. Now if I calculate the magnitude of this vector field, I'll get an algebraic equation in terms of x, y, z. Anyway, vector field has algebraic equation in terms of x, y, z, but it has x, y, z component. Those are again function of algebraic equation, fxy, gxy and hxy. Now if I calculate the magnitude, I'll get a velocity vector's magnitude, that is single algebraic equation. Now if I integrate, then I'll get the algebraic equation of an area. Keep changing x and y, then from origin that much area it is covering. This is what we saw. Now if that is the case, then what is dp by dxy plane? dp by dxy plane is dp by dx, dp by dx, okay, its derivative along x-axis cross of the, this is dp by, if p is a vector, dp by dx is a vector, cross product of dp by dy. If I do cross product of these two, I'll get dp by xy plane. If that is the case, then that is fx square. Okay, if that is the case, then that is f minus fy, m minus fy. Fy means dxy by dy, dfxy by dy. If fxy is a function, if I have a xy plane, on that I have set of xy point. Again, each xy point I have a function that relates this xy point to a vertical direction, that is z value also. So the cross of dp by dxy plane equal to dp by dx cross product of dp by dy. If that is the case, then it would turn up into minus fy, means minus dfxy by dy I vector, minus fx j plus k. Magnitude is fx square plus fy square plus 1 square, a square root. This is Cartesian way to calculate the dp by the magnitude of dp by dxy plane. Now, if I have this magnitude, I want the calculate the surface area, then I have to calculate the area the way we discussed. So, magnitude of dp by dA, and then dA I have to integrate with dA. dA is fx. dA is x comma y. So dA will turn up into, in Cartesian coordinate, it will turn up into dx dy. So dA, okay, we are integrating magnitude of dP by dA. P is position vector. P is position vector. Okay, so P on sphere, P is position vector. P keep changing. So P is position vector. dP, differentiation of position vector with respect to xy plane. dP by dA, whatever I get, calculate the magnitude, then integrate with dA. dA is xy plane. dA is xy plane. I mean it. dA is xy plane. So I have to integrate this dP, magnitude of dP by dA with xy plane. If I integrate it with xy plane, then I get the net surface area. That is the concept. Now suppose for a sphere, the equation of the surface for a sphere is x square plus y square plus z square equal to a square, where a is the radius. So z is equal to a square root of 1 minus, a square minus x square minus y square. Okay. Now what is the magnitude of dP by dA? dP by dA is fx square plus fy square plus 1 square square, because dP by dx is minus fyi minus fxi. Okay. dP by dx is P is xi plus yj plus fxy k. dP by dx is I plus fx dfxy by dx fxk. dP by dy is j plus fy k. If I do cross product of these two, it will result in minus fyi minus fxj plus k. If I calculate the magnitude, it would be fx square plus fy square plus 1 square square root. If that is the case, now for the sphere, it is x square plus y square plus z square equal to a square. Then fxy equal to a square minus x square minus y square square root. If that is the case, then we are now free to calculate the surface area. So fx square. So fx is, if fxy is square root of a square minus x square minus y square, then fx dfxy by dx is minus x divided by a square root of a square minus x square minus y square. Fy is minus y square root minus y by square root of a square minus x square minus y square. Then if that is the case, then we will substitute in a square root of fx square plus fy square plus 1. If that is the case, then it will result in x square divided by a square root of a square minus x square minus y square plus y square divided by square root of a square minus x square minus y square plus 1. Now if I do here and there, it will turn up in a by square root of a square minus x square minus y square. Integrating with xy plane, then dual integration sign. Since it is a xy plane, then or we can integrate along the xy plane. So xy plane, the xy point I am taking, that is a closed circular region, because xy would come from set of point that belongs to a closed circular region. You remember this sphere. If sphere is centered on the origin, if sphere is centered on the origin, then top hemisphere is above the xy plane, bottom hemisphere is below the xy plane, and its origin, its center is at origin. If that is the case, then on the xy plane, the set of xy we take, that is a closed circular region. So I have to integrate with the closed circular region, and that is a by square root of a square minus x square minus y square dxy plane. Okay. Now one approach that we saw through Cartesian, what we talked it, that we did, that now x I take a sine phi cos theta, then y as a sine phi sine theta, and z a cos phi. If I substitute it in x square plus y square plus z square, it turns up as a square, that is equal to a square. So it is valid now. If that is the case, then dx, if I differentiate x with phi, then dx becomes a cos phi cos theta. Now here 1 by a by square root of a square minus x square minus y square is nothing but z, pure z, because x square plus y square plus z square equal to a square. Z means a cos phi, top cos phi, bottom cos phi, top A, bottom A, all got over. So earlier the equation is a by square root of a square minus x square minus y square. That turn up into a cos phi, a gone, and dx equal to a sine a cos phi cos theta. So there cos phi gone. So now it came as a sine a cos theta d phi. If it is d phi, integrating, now the area, we are integrating with dxy plane. Dxy plane I converted into dx dy, but we will be very serious about dxy plane. This is for the sake of Cartesian coordinate. So dxy in xy plane, if I talk about dxy plane, then it is x-axis and y-axis as far as Cartesian coordinate is concerned. So dxy converted to dx dy, where dx is a sine a cos phi cos theta. We differentiated with the phi. Now cos phi gone away, a cos theta d phi. So a phi cos theta. So a phi cos theta. So a phi cos theta, if I consider cos theta as constant and some value, then it would turn up as sine inverse x by a. If a sine phi cos theta equal to x, then a phi cos theta would be sine inverse of x. This is what we are talking. Someone has to prove this. If there is some discrepancy found in this, he can proceed in this fashion. Now, if that is true, then sine inverse of x, now x is from minus a to a, then it is sine inverse of, then it turns up as sine inverse of x. Okay. Now, when x is kind of minus a to plus a, then what is sine inverse of minus, sine inverse of a and sine inverse of minus a? Okay, so someone can, I believe someone can, so this is the way, through this approach someone has to proceed on. Okay, so a sine phi cos theta equal to x, then phi we consider it as sine inverse x. If that is true, then sine inverse x is the net integration, and then sine inverse x I have to substitute a, and the limit is minus a to a. Then sine inverse of a is, so if a is constant, I can take it out. Then sine inverse of minus 1, sine inverse of 1 is pi by 2. So net it will come as a pi, a pi. Now that side dy, if I keep at dy only, integration is y, and then minus a to a means it is 2a. So 2a into a pi, 2a square pi, that is the top hemisphere, 4 pi a square. This is the approach. If there is some discrepancy, then someone can proceed in this direction. There is there there is another way. There are tons of ways when we know that our calculation of surface area is integration of the closed region, circular region, integration of the closed circular region with magnitude of dp by dxy plane, dxy plane. This is the net integration. I would repeat, magnitude of dp by dxy plane, whatever comes that magnitude, that is a by a square root of a square minus x square minus y square, integrating it along dxy plane, where integration happens in the closed region, circular closed region. Circular closed region, we saw that circular closed region is a region where this sphere is cutting the xy plane. Xy has to be taken from the closed circular region only. That is the dxy plane, that is dx. Now integrating in the closed region. One way through Cartesian we saw. Another way is we talked that is hybrid Cartesian and polar coordinate. Hybrid Cartesian and polar coordinate means d, we are integrating with dxy plane. If it is dxy plane, then in polar coordinate we have, if there is a polar coordinate, then we saw in polar coordinate, then it is 2D coordinate. Polar coordinate is 2D coordinate, and the spherical coordinate is 3D coordinate. Polar coordinate is 2D coordinate, then spherical coordinate is 3D coordinate. So if I have a kind of or if I have a xy plane and I have a circle, in xy plane I have a circle. If I have a circle, then this is the, if I have a circle, then this is the radius. If this is the radius, then there are two orthogonal components in the xy plane as far as polar coordinate is concerned. One is radius. Radius means radius starts from center, it keeps growing, 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 growing. The way it is growing, the circle is becoming bigger and bigger and bigger. So this is one way radius is moving. Another is perpendicular to the radius. Perpendicular to the radius is the circumference. So there are two orthogonal components. One is radius and another is circumference. So if at any moment if radius is r, then and if I have a movement of theta from the r, then circumference is r theta. Okay, so the area what we are calculating is multiplication of if it is x coordinate and y coordinate, then x into y is the surface area. So if it is r and r d theta, then surface area is r square. R, one is r and one is r theta. If that is true, then it is r square theta, r into r theta. Or rather, I would say if it is r, and then it proceeded small distance, then it is dr. If it is r and then it made a small progress, increment in length, then next length is dr. If this is r and in another coordinate it made a theta movement, then the arc is r d theta. So for the small strip what we are seeing, the area is r d theta dr. r d theta dr. The way we say dx and dy, here it is r d theta dy. r d theta, where angle is d theta and radius is r. So arc length is r d theta. If d theta is 2 pi, then arc length is 2 pi r. If theta is d theta, r d theta. If it is arc is r d theta, and if this is the arc, that is r d theta, and there is a dr distance, then this strip's area is, I said that two component per two vertical component you have to multiply to get the area. Then it is r d theta dr. Now we'll go back to our calculation, that what is the net surface area, that is the integration of a closed circular region a by a square root of a square minus x square minus y square dxy plane. Now dxy plane now change into, okay, so dxy plane. So dxy plane, now it is changed into r d theta dr. D of xy plane. So xy plane, dxy plane is r d theta dr, or I can say r dr d theta. Now here a by square root of a square minus x square minus y square. Now this I have to change it to Cartesian coordinate, Cartesian to polar. So if it is r theta, if this is r, if this is r, if this is if this if if this is r, then x component is r cos theta, y component is r sin theta in polar coordinate. So now it is replaced by a by square root of a square minus r cos square theta, r square cos square theta minus r square sin square theta. That would result in a by square root of a square minus r square on top r dr d theta. Now someone is free to calculate AR divided by square root of a square minus r square dr. Once you integrate it, then place r 0 to a, because a is the net radius. So 0 to a and see what it comes. Then again integrate with d theta, and theta you integrate with 0 to 2 pi. Whatever you get, probably you will get for the top hemisphere, you multiply by 2, you will get 4a square, 4 pi a square. So this is nothing but polar Cartesian hybrid. Now we'll talk about spherical 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 Cartesian hybrid. Cartesian polar hybrid we saw. Now we'll show uh, car, spherical Cartesian hybrid. This is our approach, not available anywhere else. This is our approach and not available anywhere else that you can check. Okay, so this is Cartesian spherical hybrid model. Now in Cartesian spherical hybrid model, what is this model? Now let's go back and see what is the net integration. The net integration what we see is integration in the circular closed loop a square by a square root of a square minus x square minus y square dxy plane. Okay. Now x is, you remember that x is a sine phi cos theta. A sine phi cos theta that we had thought earlier. A sine phi cos theta. Y is a sine phi sin theta. Z is a cos phi. If I substitute in equation x square plus y square plus z square, it comes as a square. That is what the equation is. Now this is a spherical coordinate system. If this is a spherical coordinate system, please see our video on the spherical coordinate system. So if I have a if I have a sphere, if I have a sphere, then if I have a sphere, then then in the sphere, this is the sphere. If this is the sphere, this sphere is centered at the origin. If this sphere is centered at the origin, then from origin at any point P, if I draw a line from origin, any point P, if I draw a line, that is the radius. Consider that radius is A. Consider that radius is A. If that radius is A, then if that is the radius, till slant radius, then it makes phi degree from the vertical. This is a spherical coordinate system. It makes angle phi with the vertical. It makes phi with the vertical. Okay. Now if it is A, if it is A is the radius and phi is the angle, then its essence on the xy plane is A sine phi. Now A sine phi is the radius on the xy plane, but it would not touch, it is not A. A sine phi is less than A. So if it is a sphere and there is any point P, then from center if I draw a line to P, it is A radius. If this is radius and this is vertical component, then it makes phi degree from the vertical. A cos phi is the is the horizontal component and A sine phi is the vertical component that falls on xy plane. If it falls on xy plane, on xy plane I have a on xy plane if I have a circular region, then A sine phi will not touch the perimeter. It will be less than that as per the phi. If phi is 90 degree, then A sine phi will be A. Otherwise, it will be less than A. Okay, now what is, again we'll go back to the integration. Integration is integration of a by square root of a square minus x square minus y square dxy plane. Now dxy plane, now we saw dxy plane, if I want, then I have to have r d theta dr, r d theta dr, because that is the xy plane in a spherical coordinate also. So in a spherical coordinate, finally we land up in the xy plane as far as r sine phi is concerned. If it is r and it is phi, then this is r cos phi and this is r sine phi that falls on the xy plane. Now r sine phi cos theta is x-axis. This is what x we have taken. R sine phi sine theta, if it makes theta degree with the x-axis. Now we have three axes: x-axis, y-axis and z-axis. If this is the radius A and makes phi degree from z-axis, then A cos phi is the z-axis. A sin phi falls on the xy plane somewhere. A sin phi cos theta is the x-axis. A sin phi sin theta is the y-axis. Now what is the radius? Radius is A sin phi. A sin phi. R d theta. R d theta is the arc length. So A sin phi d theta. A sin phi d theta into dr. Dr, if I have a radius r, then dr. What is radius r? That is a sin phi. Dr, differentiation of r. So r is a sin phi. A sin phi. Then dr is a cos phi d phi. Now I have now r d theta dr. R d theta is now a sin phi is r. So a sin phi d theta r cos phi d phi, because dr means differentiation of r. R is a sin phi, then dr is a cos phi d phi. So now we came to a sin phi d theta, a cos phi d cos phi d phi. This solution is not available anywhere. You can search. Now I have integration in the closed region, circular closed region, a by square root of a square minus x square minus y square, a sin phi d theta, a cos phi d phi. Now x square a square, now we have another equation, that is a x square plus y square plus z square equal to a square. So z square equal to a square minus x square minus y square. If that is true, then a by square root of a square minus x square minus y square would turn up into a by a a cos phi, a by z. A by z means a by cos phi. A gone, 1 by cos phi. 1 by cos phi. Now this side we have a sin phi d theta, a cos phi d phi. Cos phi also gone. Now I have a means a square sin phi d phi d theta. At the end I have a square sin phi d theta. So integration of sin phi is cos phi. Integration of sin phi is cos phi. Cos phi limit is, if it is phi degree from vertical, then it would go from 0 to pi. Then full it will take care, 0 to pi. So if I have cos phi 0 to pi, then it is 2. Cos 0 1, cos pi is minus 1, 2. Now I have 2 a square. Now d theta integration is theta. when theta on the xy plane rotates 2 pi degree, then we get phi from 0 to pi and theta from 0 to 2 pi. If I integrate full sphere area, I am getting. So 2a square into theta integration is theta from 0 to 2 pi would 2 pi. 4 pi a square. This is the most straightforward that we will file disclosure on it. So both Cartesian, one approach we showed that was pure Cartesian way, and this is Cartesian a spherical hybrid model. So we have seen that. I thought that I would finish it. So a spherical coordinate we will do in the kind of last session. I will have one more session, and there we will talk about the pure Cartesian once again. Like I'll take a example of a cube, and then I'll calculate the surface area or cube in the sense cuboid, that would be rectangle or pure cuboid, and then pure 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 spherical coordinate. We took spherical spherical Cartesian hybrid. Okay, but now we will take pure spherical coordinate, because sphere can be addressed in pure spherical coordinate. Sphere cannot be addressed in pure polar coordinate. The polar coordinate is only on the xy plane, but it can be addressed in pure spherical coordinate. So Cartesian spherical hybrid model, that we have invented that approach, so that we saw. Now we will see the pure spherical coordinate and pure Cartesian coordinate, where we don't need cos theta sin theta. So pure Cartesian coordinate. So spherical coordinate, polar coordinate. We saw that xy plane, xy set of xy value is confined to a closed circular region. If it is confined to a closed circular region, then this is a kind of a customer of client to the spherical or polar coordinates. So pure spherical and pure Cartesian, where we don't need any theta beta. So both, one we will calculate again a sphere, and another we will calculate the cuboid. So that we will see in the next section. But with the polar and Cartesian coordinate hybrid, we can calculate the surface area of the paraboloid that we have seen. That is fxy equal to x square plus y square, means z equal to x square plus y square. So the dp by dA is fx square plus fy square plus 1 square root. That would come as 4x square plus 4y square plus 1 square root integration with the dxy plane. So dxy plane is r d theta dr. Then here x is r cos theta r sin theta. It will come as 4 4 plus 1, 4 sin square theta, 4 cos square theta, 4 plus 1. Okay, if x, now x is a cos theta, so it will turn up as 4a square cos square theta plus 4a square sin square theta plus 1. That will turn up as 4a square or 4r square. So 1 plus 4r square square root, and then r d theta dr, and integrate in the closed circular loop, where r is now 0 to a and theta is 0 to pi. So this way we can calculate the surface area of a paraboloid and cone and everything, hybrid of Cartesian and polar coordinate. Through hybrid of Cartesian and spherical coordinate, very quickly we can calculate surface area of the sphere. Now where the variable is phi and theta. With polar hybrid, variable was r and theta. Here phi and theta. Now we will see pure Cartesian and pure spherical. Which is best depend upon your need. Whatever your need, understand the xy plane. What is the xy plane region on which you are calculating the surface area? If it is pure xy plane, then it is probably the Cartesian coordinate only. But if it is circular, like cone, if you take, then underneath it is circular. Paraboloid, if you take underneath, it is circular. A sphere, if you take, then underneath it is circular. So this is what we kind of we have we this is how we move forward. If something comes new, then that also we will discuss. So this is how it is that calculating the surface area. We'll proceed on